All right, so I have nothing to add about my person because you already said everything. But what I would like to add is that Fraunhofer IPMS is also a member of FMD, so we're one of the microelectronic institutes, which together with two other institutes from another association working together when it comes to microelectronics. And what I also would like to mention that you can see here my name, but a lot of the slides I will show are basically uh, based on a webinar which we did already doing a project called Green ICT, because things are still valid. And therefore, I would also like to highlight the contribution of one of my colleagues there. So what is PFAS? So we had the name PFAS already a couple of times. And therefore, I would like to start with a definition. So there's a so-called definition from the OECD, which you can see. So our world mainly consists of things made of carbon and of hydrogen, oxygen. These are the things we need. But if you now would substitute hydrogen with fluorine, so then you're having PFAS at the end. So PFAS is not one substance. PFAS are millions of compounds, and not all of them are used at industry today. We have around like 7 million compounds, and around 2 times 500 are unused. And you can see the formula on the right-hand side. So you have the carbon atom in the middle, and then you have the fluorine, which is attached to that. So that is like the definition of PFAS, basically. What you can also see is a pen there. So, so one of the first PFAS which was used was Teflon. Teflon is a brand name for that PFAS, and well, originally it was used for atomic bombs, but then they found out that it's very non-sticky, which is really nice for getting your egg out of the pan afterwards. Therefore, it's nowadays used for pans. Well, that is okay until you do not heat it up too much. So if you heat up your pan, your empty pan, above 360 degrees Celsius, I would recommend not to do that, because then you might have problems with toxic gases. So, but back to PFAS, you can see it's a big group we are talking about. At the end, the carbon fluoride bond is very important. So you can see the drawing of the carbon atom, and you can see the fluorine, and they are bonded due to the dipole moment. So maybe you can see the plus, and you can see the minus. And it has to do with fluorine is the most electronegative element there. So it's really a strong bond. And you can even see a proof of that by looking in the table. So you can see different compounds. So in the first row, this compound has 1F. Then the second row, 2F, then 3 and 4 at the end. If you now compare the length of the bond between the carbon and the fluorine, you can see that it starts with 1.385 angstrom. And if you would take a look at the last line, it is reduced 1 to 1.319 angstrom. That has to do with the amount of fluorine. So basically that means the more fluorine you have there, the shorter the bonds are. The more hydrogen you substitute by fluorine, the shorter the bonds. The more fluorine you have, the more stable your compound is. This is given by the bonding density given at the last column. You can also see that this is increasing with the amount of fluorine you have. So why do we use PFAS at all? First of all, it's very unreactive, which is kind of good for a lot of things. It has high binding energy, which you can see in the table. And this leads to a couple of other properties. So it has an extremely low surface energy. Therefore, it's highly polar surface. And now comes something which is very unique. On the one hand side, PFAS is it is hydrophobe. That means the contact angle of water, for example, on Teflon is very high. So, and on the other hand side, simultaneously, you cannot wet it by oil. This is very unique to have both of these things, oil and water. So first come to the upside. PFAS has favorable electronic properties. It is extremely pure, has low friction, very little abrasion. It's very thermostable, and is a source for highly reactive fluid species for reaction, for example, with silicon. And it's also a source for strong acids, which you need, it has low refractive index, it's good UV transmission, and a very broad and high chemical resistance. And because it does not have only one of these properties, because it has all of these, this is very unique. It's very challenging to find materials which fulfill all of these properties at the same time. Now comes the downside. The downside is that it is a persistent organic pollutant. That means it accumulates. If it's there, it's there. So if it's once it is in the environment, it's just there. It's really hard to get rid of it again. And it accumulates. And on the other hand, it's a health risk for us, for humans. Can lead to cancer, liver issues, fertility issues, cholesterol. So a lot of negative effects we don't want to have. And of course, for every living organism. And also PFAS it binds to blood proteins. I will show there's a study showing that PFAS can be found, for example, in Germans between the age of 3 up to they only looked like children, but already at the age of 3 it was possible to measure PFAS in blood of Germans. And one reason why might be because we consume, for example, fish, eggs, and of course we drink water, and PFAS is already present there. One thing which is not PFAS, but PFAS slowly goes over time to TFA. This you can also find everywhere. Even in diluted solution, this is still toxic for water organism. And this is like the most abundant PFAS found in the environment because it's spread in the rivers and waters. That's why I would like to give it a separate slide. And you can see Europe. You can see a lot of red dots. So every red dot there is a measurement. Every blue dot there is a presumed contamination. So every red dot is a contamination. So basically, what they did was they took random sample of 23 surface waters and groundwaters, different 10 European countries, and they detected PFAS everywhere. So 98% of PFAS was TFA, which I told you before is the most great. I cannot pronounce it. You just read it. I won't pronounce it again. And you can see that 79% of the sample exceeding the drinking water directive. Which, for your information, the drinking water directive is not applied to surface water, but just to have some kind of reference value. That's why they took that value. And also the TFA levels, they have a big range. So it can be low to 370 nanogram per liter and up to 3,300 nanogram per liter. And the more it is, the worse it is. And that means that TFR at the end is kind of the most largest known widespread water contamination of a chemical until now. That means basically we drink PFAS daily. But still, PFAS has a lot of advantage for semiconductor. You want to say something or? Okay. And I would like now to tell you why it is used in semiconductor and why it is also so complicated to get rid of it. First of all, PFAS is not only present in semiconductor. Basically, if you look at different sections in Europe, you can see that semiconductor only is like an amount of 1%, which does not mean that it's unimportant. I do not want to stress that out. I only would like to inform you that also in other sections like textile, paper and packaging, or even firefighting form, PFAS is present. And of course, they also look at that or should look at that and think about what could be done to get rid of PFAS. And if you look at the graph on the right-hand side, you see quite a big green part. This is again, PTFE, which is the brand name was Teflon. So this is around 60%. And the other orange one, for example, this is specific PFAS, which is, for example, used for O-rings and tubes and semiconductor fabs, but also, for example, for strings in guitar. So that just to emphasize, we do use PFAS in quite a lot of different sections already. Where do we use it in semiconductor? So we use it in process chemicals, and I will, in a few slides, will explain some of them in more detail, just for you to get an overview. We don't have the time to explain all of them in detail, but there are a lot of different processes where we can look into where PFAS is an important part at the moment, and it doesn't need to be in the future. So process chemicals, which you need for etching, for example, for the lithography, different instruments. They can be part of the machine, but in a fab, you have like the machine is situated in a clean room, so in a very specific environment. And even there, the fab infrastructure, you might have some O-rings, which are PFAS contaminated, or what at the end comes out of your fab that might also have PFAS because we need glue, we need cable, and so on. Or to get an even better overview, so just think about like a semiconductor fab, like a lot of machines, and you use for one product, your wafer is running through these machines not only once, a couple of times, depending on your final product. That means, for example, lithography is a very standard procedure for semiconductor processes. There you have PFAS. I will go into this example with more detail on the next slide. Then we have also wet chemistry for chemical mechanical polishing, for example, where PFAS present, wet cleaning, wet chemical etching, and also for plasma applications, so dry etching, chemical wafer deposition. I don't expect that you know immediately what it means. Just to give you an overview, that it's for a lot of important processes in semiconductor at the moment, PFAS is important and present. And also at the end, so if you start with your wafer, at the end, before you like get it out of the fab, you will do assembly, test, and packaging. And there you have it again. So packaging fluxes, for example, or thermal ionization, mass spectrometry. And also the articles which come out can have PFAS. I would like to slow down a bit and explain you one example. So photolithography means basically if you have a sample, if you have a wafer and you would like to have certain areas structured, what you basically do is you put a so-called photoresist on top of it. That would be like, it would cover your complete wafer. And then with a different machine, for example, you could use UV light, you can write specific patterns into that. Then due to that, you will have it that way that only the areas which you wrote, or if you use the mass, only the areas which were exposed, they behave differently compared to the non-exposed areas. That means you have like a mask at the end. Your mask is written in the photolithography film. And then for the example, maybe the next step would be that you apply another material, another metal, whatever. And then it only will be at a certain area you choose before. So photolithography is very important for every kind of chips to have specifically defined structures. And unfortunately, photoacid generators, which are used for this process, they have PFAS because we have a specific properties which we need. They need to be very stable. They need to have a good solubility in solvents, and it needs to be a strong non-nucleophilic acid, and it needs to behave certain to UV light because it's what we use for structuring it at the end. You can see a table on the right-hand side, and there is in the first, or better to say, in the first column, basically are the desired properties, which are kind of already set to you before. And in the second column, you can see what is used at the moment. So the PFAS, which is used in photoacid, is fulfills all of the desired properties. And now we come to the problem. So on the one hand side, we would like to get rid of the PFAS because it has a lot of negative effects on environment and humans and other living species. On the other hand side, for example, if you look at the middle column, you can see that the first one is poor when it comes to photo speed, and unfortunately it's not transparent to the specific wavelength. So you need to kind of figure out what works the best to, on the one hand side, about the environment, and on the other hand side, you need to be sure that these processes are still working out. Another more specific example is the anti-adhesion coating. First, maybe we take a look on the sketch. So what you see there is a so-called CMAT. CMAT means it's a capacitive, or affordable in English. I will explain to you what it does. So you see, you have two electrodes. So the bottom one is rigid, so it's like stable, and the other one is a membrane, it's flexible. So we can operate it in two ways. So one would be we change the voltage, and then the membrane starts to move. And due to the movement of the membrane, you create a wave. In this case, in this range of ultrasonic wave. So basically, it's like a loudspeaker, for example. If you think about that, you could also operate it in the other way. that the membrane is not moving and there might be an incoming sound wave. And this incoming sound wave changes your membrane. And this movement can be detected by the change in voltage. So it works both ways. But to work that way, it is very important that it has a specific coating. Otherwise, we get in trouble with water, and then it basically ruins the sensor. And there are two ideas, two techniques to get this specific coating. So one is chemical vapor deposition. That's a technique where you can have very defined coatings to make it very simple. Atomic layer deposition is even more specific. It's slower, but it's really like very, very specific. You can do very well-defined surfaces. But now comes the question, what kind of surface you would like? So current standard was PFAS, which gives you the desired properties of kind of getting rid of the water. You can see the hydrophile properties is the one which is important for this sensor. So one idea would be to substitute that with a different PFAS, with FDTS, because in this case, you do not need so much of that. So maybe sometimes substitution with a PFAS and you need less is already maybe going in the right direction. So I have 5 more minutes, enough time for the rest of the slides, and for another example. Another very standard process in semiconductor industry is the so-called deep reactive ion etching. It's also called by, you can also call it Bosch process. So it's like, you can see like not top down, you can see it like from the side. Just think about your wafer is like the blue box. It's made of silicon. Silicon is very typical. You put a resist, so maybe a photoresist on top of that. And now you would like to have a specific tunnel where you have that gap between the gray areas for some kind of reason. And what is important for a tunnel is that it really goes only like downwards. It's not spreading in all directions. So that this is called anisotropic. So anisotropic means that it has a defined direction. So you would like to have the etching only downwards. So that is for this, typically you'll use fluoride containing etching gases because they have that property. And for example, use CF4F8 in argon in plasma. And you can see that like they put that coating on top of that and they do the etching, and over a while it gets deeper. So how it looks at the end, you can see it in the SEM picture on the right-hand side, upper corner. So you can see now we have already 3 examples where PFAS is widely used, and I hope you get a feeling of why it is important for semiconductor at the moment. I'm not stressing out that it should stay that way, but why we use it. So it comes to the question how to get rid of PFAS. There are different solutions for that. So one could be we could use abatement, which is already partially done already, but maybe that could be even better. So gas scrubbers, water treatment, and so on. Or to substitute that. Substitution would be the best solution, but to be really honest, I do not expect that it is always possible because you have the imbalance between economically favorable and process optimization. And then another one would be, well, if we need to use PFAS, how could we recycle that? Is that possible? Well, at the moment, it's not possible for all of them at all. And then restrain would be the last option. And this may be the worst option. This could be done, but we will see. So take-home message would be, so PFAS properties are defined by the carbon fluoride bond. I showed you at the beginning, if you remember the carbon and the fluoride. So this is like the main definition of PFAS. The properties PFAS has are very well suited for microelectronics and also other industries, and they're difficult to replace, as at the moment there might not be a substitution material yet, underlined yet. PFAS accumulate in the environment and are often toxic. So that means we are somehow caught between the conflict of interest of lobbyists, regulation, and people, and I really would wonder how it will end. And at least we must prevent their release into the environment, and better still replace them whenever it's possible. With this, I would like to thank you for your attention. And of course, my institute is working on that, and we are really looking forward to get in touch with you. Thank you.
So
All right.
Julia already mentioned what is the definition of PFAS. I'll be talking today about why substitution of PFAS matters and why it's so important. And I'll talk in a very general way. And whenever there are very specific examples for semiconductors, I'll mention it. And why I want to come back to the definition is that this definition it's relevant within the EU, so it's something that the EU level decided to take this definition for PFAS, and it's very important because it's a very inclusive definition. So it potentially includes over 10,000 different substances, and it's much more inclusive than previous definitions. By comparison, the red circle that you see in the graph when it was suggested as a definition for PFAS only included around 200 substances. And for semiconductors, this matters a lot. Taking as one example, CF4, which is used in many processes, would be considered as a PFAS and therefore potentially regulated by the EU. So how does PFAS affect us? Why is it important to replace it? So lately there are many headlines, as Julia mentioned. For example, PFAS in water in the EU, in firefighter foams, which was a huge industry that contained PFAS. PFAS leaching into the soil in Belgium, for example, and more lately, even PFAS or athletes in the Olympics being banned because of the wax used in their snowboards. So it's getting a lot of attention. And one example, very concrete. So I'm based in the Netherlands. And recently there was a study from the Dutch government which concluded that most Dutch people have PFAS in their blood. And this is because it's highly bioaccumulative and its half-life is approximately 5 years. So even if you found a way to stop intaking PFAS into your body, it would take a really long time for you to be almost PFAS free. So this is one of the very important properties of PFAS when we talk about human health. And as Julia also showed, how mobile is PFAS? This is another important property of PFAS. So PFAS are very stable molecules, and they're also very soluble in water. A lot of them contain part of the chain, which makes them soluble in water. And because they don't degrade, basically the water system is going to dictate how far it's going to travel. And because in Europe, water systems are very interconnected, it can travel very far. It can seep into the soil, for example, from water, and it can also travel through the air. One example is in incineration plants, when they try to get rid of PFAS by burning it, the process is not always complete, and smaller chain PFAS make it to the air. And in our lives, how widespread are they in our consumer products? So there was a study done by the Committee on Consumer Safety, and they found that about 1 in 5 items contained PFAS. The 7% they didn't. It's considered PFAS, but they didn't take it into account because they couldn't exactly get down to the specific PFAS that was there. And out of this, 21%. 12% were already restricted from 2026, and 9% were already illegal. So even the regulated PFAS make it into consumer products. Some of it are unidentified. We'll get to that in a bit. But phase out is ongoing as most of the products are PFAS free. So what are some of the issues with PFAS and why that matters? Why it's important to substitute them. So PFAS is a very particular group of chemical substances because there's still a lot we don't know about them. Usually when substances are regulated or when they get a lot of attention, it's because there's a mountain of evidence on them, But PFAS is so complex and there are so many substances. There's still a lot of things we don't know about them, but this don't make them less relevant when you talk about regulating or substituting. It can even make them more relevant because the unknowns are so big and the potential risk becomes so big. So some of the challenges with PFAS is because it's very hard to monitor. So if you can't monitor PFAS, it's also very hard to detect PFAS. As I mentioned, it's a huge group of molecules, and only very recently, very strict analytical methods have started to look into trying to analyze as many as possible. But because they are so diverse and especially smaller PFAS, it's extremely hard. As one example, in the lab, there aren't even references available to compare your analysis with. So without a reference, it becomes even hard to analyze it in the lab. For the semiconductor industry, this becomes hard because the matrices are very diverse and uh, they can be very acidic, they can be very basic, so it makes analysis also hard. And even when you do analyze them in the lab, it's very costly and very slow. When you try to abate PFAS, also for the semicon industry, currently usually requires a lot of energy to abate PFAS. For one example is electrical chemical destruction of PFAS, which is not currently very feasible because it takes a lot of energy, therefore you generate greenhouse gases, and this offsets any benefits of any environmental benefits. A lot of processes use a lot of water, which offsets also environmental benefits. Even when you do exclude them, so you filtrate them, for example, you still have to then get rid of their PFAS that you concentrated either in water or in a solid matrix, and then you have to destroy it. And as I mentioned, incineration of PFAS can be very complex and it can generate byproducts. So that is also extremely hard. And when you try to substitute, as Julia mentioned, it's extremely hard to substitute because it's a high performing material with many desired properties for the semicon industry. Besides that, the raw product of PFAS comes from fluoride, which is a natural mineral, and it's considered as a, uh, as a material that can be very hard to obtain because it's usually sourced elsewhere. It's usually regulated, so it creates risks in the supply chain, which for the semicon industry also creates risks in producing semiconductors. So what are the drivers currently to move away from PFAS? So we're going to look at legislation, we're going to look at research, litigations, and advocacy. So how are PFAS regulated worldwide? So maybe the main driver for companies or any business to get rid of PFAS are legislations. And it's usually regulated through three different types of mechanisms. You can have sector-based, so you have PFAS in food packaging, for example, and you regulate within that one application. You have group-based, which is a type of PFAS or a family of PFAS, and then you regulate that family, which has certain properties. Or it can be through compliance. You can say uh, Drinking Water Act. So through a Drinking Water Act, you also regulate PFAS. So it's compliance-based regulations. And here I put some examples on how it's done, and it's very similar for the EU. So you have compliance, which touches upon how you can import, how you can discard, what are the supply chain documents you need, or PFAS cannot be above or below this limit in the water, in drinking water, in biosolids, and so on. You have certain types of industries, and usually these industries, the first ones to be regulated are the ones that have higher risk for human health. So you have textiles, they come in contact with skin, or firefighter foams, because that's a very legacy problem with PFAS in cosmetics, in dental floss. So you have industry-based bans, and then you have class-based bans, which is a group. So the biggest class of PFAS that were regulated were the longer chain PFOS and PFOA, and then you say these two or these group of PFAS can't be used or have to be used in a certain way. But this creates a problem which is that you substitute one PFAS with another PFAS. And here, as an example, with PFOS and Gen X. So PFOS was introduced in the market around 1938. And around the 1990s, there was enough evidence of risk that PFOS was harmful to health. And in 2009, it was regulated. And in the same year, Gen X came into the market to substitute PFOS as a direct substitute. And in 2015, there was enough risk, recognition of risk. And in 2009, it was regulated. And this is all within the EU. So these windows do get shorter as the scientific community gets used to working with PFAS, as legislators get used to working with PFAS, but it will probably never be small enough because innovation is always going to outpace legislation. You can always create a different PFAS, which is not in that group that is being regulated. So in 2023, the EU came up with a restriction proposal, which is a universal PFAS ban. And I won't go into the process, but I'll mention two of the motivations of the member states which proposed this universal PFAS ban. And they argued that they cannot come up with a value of PFAS which they accept the risk. So they put PFAS as a non-threshold substance. That means that they cannot say above this limit PFAS is unsafe and below this limit it's safe because of all the unknowns that I mentioned earlier. So they say that any concentration of PFAS is an unacceptable risk. And they also argue that there are enough stocks in the environment that exposure will last for generations. So this is where the unknowns and the potential risk comes in. Another process is litigation. So litigations are usually lawsuits against governments, against businesses. And this is also a huge motivation for the industry because it poses high risks for operations, high risks for revenue. And I'll leave on the slides. There are many examples in Europe. There is in the Netherlands with Chemours company, in Germany with 3M, Belgium also 3M, Italy with the local municipality, France, and so on. So there are many examples, and this is also a big driver for change. And also motivation to do research for alternatives or sensing or abatement of PFAS. And this is a graph I made this morning. I have a table which I keep track of EU funding opportunities, and relatively, this is a percentage relative to the total of each of all the years. And in 2025, 40% between 2020 and 2025 were projects, 40% of projects were in 2025. So the EU is promoting research into this topic because of its growing relevance. So this is also a big drive for change, but also advocacy. So when I talked about the definition of PFAS, there was a lot of lobbying to try to change the definition to make it less inclusive so that it includes fewer substances. And actually, researchers led by Gabriel, which is a researcher here from Wageningen University, where I'm based, made a statement defending the definition so that the EU wouldn't change it. You have groups like the Forever Pollution Project, which is where the graph that Julie and I showed of pollution in Europe came from. So those are journalists, for example, which made that graph and tracked PFAS across Europe. And you have the Corporate Europe Observatory, which tracks lobbying within the EU, and they have a separate group just for PFAS. So what would be the cost of PFAS in the EU? It could potentially be 40 billion a year in health costs. And these are really underestimated because they only tracked 4 PFAS amongst all the possible ones. And under business as usual, we would have 10,000 contaminated sites within Europe. So this is really a big, these numbers, which were in a report commissioned by the European Union, is a big motivation for the EU to move away. In the same report, and here I want to leave an open question, they they track the pathways which PFAS could potentially impact ecosystem services. And if you don't know, ecosystem services are the direct and indirect contribution of ecosystems to human well-being. So you could say, for example, that many of the water bodies we have are clean because of the pathway they take. They naturally are clean water bodies, the whole water cycle. For example, this costs us nothing. It's something that ecosystem services provides. And in the very last column, so they trace back PFAS in water and PFAS in soil and how each step could lead to the failure of an ecosystem service. And they trace back to, for example, loss of drinking water, loss of carbon stocks, loss of productivity, loss of fisheries, loss of opportunity in fishing, and a lot of it is tied to capital. So a lot of it is tied which ecosystem services produce a risk to capital, but not necessarily ecosystem services risks are linked to capital. Many of it should be linked intrinsically to the value of nature. But anyway, here they pose it a lot related to capital, but it's an open question to you on ecosystem services. So what I tried to show is that even though it's extremely hard to replace PFAS, and in some cases it looks quite impossible, there are still hopefully ways which we can use it, and like Julia mentioned, maybe recycle it, maybe isolate it, so that it doesn't make it into our environment. And just in the usage of PFAS itself potentially causes leaks in production. So the ultimate goal also that we have as an industry and in Genesis is to move to a PFAS-free future. And that's it for me.
Thank you, Pedro. Thank you so much. I think it's always great to understand about PFAS and their role in the industry. For the last part, I think it's back to you, Julia.
Yep, I will show only a few slides again.
Yeah.
So I have the feeling that at least it seems to be a little bit not depressing, but it does not need to, so there's chances that we have the chance to keep things change for the good now. So it means there's still, it's not lost, right? So therefore also in Genesis, PFAS is a big issue because Iranda already showed you some slides. I just will add some comments. So I cannot tell in detail what exactly we're doing there at the moment because the project is now in phase 2. That means the project is 3 years long. We have 1 year we already managed. And I think when I read out already the main goals, that means I will go to the PFAS related topics. So in Genesis, we're working on PFAS sensors because detection at the moment is actually a big issue, especially in semiconductor fabs. It really depends at which time do you check your wastewater and after which machine. So ideally, also there, or maybe at the end of a fab, would be to have a sensor which tells you in real life there is this kind of PFAS. That would be great. For sure, it won't be this one and only sensor. It might be at the end different sensors. That's also why in Genesis we're working with different sensor concepts to detect different PFAS molecules, because it's really from the detection point of view, it's different if it's short chain PFAS or long chain and so on. Oh, I found error, don't worry. Also, abatement is an issue which can be better than it is at the moment. It would be great if we get, in case we need to use it, get it out of the air before we pollute it. Also abatement in water. So we have 4 different approaches. And the good thing about Genesis is that it's not only RTOs and university working there together, there are the big fabs in the project. That means we have access to real fab water. We have also the possibility later on in the project to test it under real condition. So we will see how much progress we make, but this is really the goal. The goal is to have something reliable, which we test in the fabs. And for this, also characterization, which is I think part of work package 3, is also another issue. So PFAS and PFAS materials. I would like to show you one example, which we shared already on Silicon Saxony days last week, I think. So where we have already the motivation about PFAS. And the problem is, for example, if you have PFAS in water and you would like to get rid of it, one idea would be to use graphene oxide. This partially works already, but it does not work as good as you would like to have it because the absorption rate is too low. Therefore, the goal in this project was only one tiny part of this huge project, but in specifically this subtask, they would like to enhance the PFAS absorption of graphene oxide. And here, for example, you can see already a first measurement, which I will explain to you now. You can see a lot of colorful graphs. On the y-axis, you can see how much PFAS was captured in percentage. On the x-axis, you can see the amount of PFAS concentration. So there's wastewater stream coming in of 5.4.9 ppm. You can see it flows through the first stage. And in the lightly gray color, it's at the bottom, you can see it's already reduced quite a lot. So now it's only 0.77 ppm. That means after the first stage, getting this PFAS contaminated wastewater running through a so-called freestanding graphene oxide, it was possible to show that they can reduce it up to 95% already. You can see three different colors because it has to do with what I mentioned before, that the chain length of PFAS also defines not only the sensing, also defines what you need to use for absorption. So here they found out that the absorption is better for long chain compared to short chain. And then they would like to reduce it further. That's why you have 4 more stages. So at the end, you have a PFAS level which is below 0.4 ppb. I mean, still, as Pedro said, there is not this one and only good value or this threshold, that's true, but 0.4 ppb is much less compared with what should start. Basically, the less PFAS, the better it is. And this was done by also partners on our Genesis project, so basically layer 1 incentive. And with this, I think I would like to stop and we're open for questions.